Right, section 7.5 deals with Hermitian unitary and normal matrices. Okay, so in this section we shall consider the diagonalization problem for complex matrices. Now remember, matrix A is a complex matrix. If a matrix A is a complex matrix, remember a complex matrix is a matrix where the entries in the matrix are complex numbers. If A is a complex matrix, then the conjugate transpose of A, and it's denoted by A star, is simply what you do is you take the conjugate of the matrix A. In other words, for each entry, you take the conjugate. Now just recall that the conjugate of a complex number, right? So if A plus, if this is a complex number, right, then the conjugate of that complex number is simply going to be the number where you change that sign there. So you'll change that in that case to a negative there. So that is a conjugate of a complex number. So what you would do is you will take the matrix A and all the complex entries, you will take their conjugates. Okay, and then of that matrix that you obtain, you're going to take the transpose of that. Now just a remark, note that the conjugate of A's transpose is simply A's transpose conjugate. Okay, so recall section 5.3 where we look at conjugation and the conjugation operation distributes over a transpose. Also for a real matrix, obviously the conjugate of a real matrix is the matrix itself, and then looking at the transpose of that matrix, that is going to be the conjugate transpose. Right, now I'm not going to do this example here. It's a straightforward application of what we just did. You're going to just take the conjugate of A, and then you're going to take the transpose of that matrix. That's quite straightforward. And just theorem 1 to take note of is just this just all these properties. If K is a complex scalar, if A, B, and C are complex matrices whose sizes are such that the status operation can be performed, then we have the following. So the conjugate transpose of the conjugate transpose is gives you the matrix A. That's quite obvious. Conjugate transpose distributes over a sum, and that's simply because the transpose distributes over a sum between matrices, and the conjugation operation also distributes over the sum. That's section 5.3. The same is when you've got the difference between two matrices. It also distributes in that exactly that way. Then over scalar multiples, again the conjugation. Remember when you take the conjugate of a that scalar could be a complex number, right? So when you take the conjugate of this, yeah, according to what we did in section 5.3, that's going to be the conjugate of that and the conjugate of that, and then taking the transpose of that is going to be the transpose of that, and again that distributes in that way. So it's quite easy to see that that is in fact the case. Okay, then lastly the conjugate distributes over the product between matrices, but just in such a way that the two switch around, just like the transpose. Remember, the transpose distributes over a product, but a little bit differently. The orders of the matrices switch around. Okay, so because of that fact, and if you look at the conjugates on both sides, the conjugates, they are going to distribute in that way. Okay, and there you've got the transpose of that. And again, from what we know about our transposes, that is just going to be switch around. So we are going to be left with that. Okay, and that is B star and that's A star. Okay, so it's basically just an application of everything we've done up until now on transposes and complex matrices. Right, then a definition that they're talking about here is the definition of a Hermitian and a unitary matrix. Right, so note that the relationship, remember the complex dot product. How did we define the complex dot product? What you do is you take the matrix, you take the column vector U and V, and then what you do is you transpose V, and you take the conjugate of V, and you dot that with U. Right, and that was defined as the complex dot product. So in the case of complex matrices, that's how our dot product is defined. And we basically you can define V bar T as just a V star. Now, a square complex matrix A is said to be unitary if the matrix's inverse is its complex conjugate. And it is Hermitian if the matrix A is its complex conjugate. Now, if A is a real matrix, then obviously it's then, and if it is Hermitian, then the complex conjugate is just its transpose. So from this we see that unitary matrices are complex generalizations of the real orthogonal matrices, and Hermitian matrices are complex generalizations of real symmetric matrices. Right, the next problem, you guys can do number 1 as an exercise, determine whether the given matrices are Hermitian or not. If we look at the second one, if we look at complex conjugate of that matrix there, first of all, if you look at the conjugate of the matrix B, that's going to be this matrix, okay. And if you look at the transpose of this matrix, okay, you're going to basically see what it is equal to. So that's going to be transpose. All right. Right, now if you look at right, so so again, what is B? What is B's conjugates is transpose? That's B star, and that is clearly not the same as B, because obviously we've got a different entry there. Okay, so that is not Hermitian. Right, so the next theorem, just some properties of Hermitian matrices. The eigenvalues of a Hermitian matrix, they are always real numbers. Right, so let's see why that is the case. Right, so let lambda be an eigenvalue of A with X, an eigenvector corresponding to lambda. Right, then we've got the following. Remember now that we have that AX is lambda X, right? So you take the conjugate on both sides. Right, so then we've got, that implies that the conjugate of A times the conjugate of X is the conjugate of lambda times the conjugate of X. Right, and then what I'm going to do is I'm going to multiply on the left and on the right, and I'm going to multiply with X's transpose. Okay, so there we go. X's transpose, and so we get that we've got that there. Okay. Right, now taking that expression, we can basically then just take this expression and replace it with this expression. Okay, that's just by transpose laws. Right, so what can we say from there? We can say from there that basically you can replace that with A's complex conjugate. And we know that X is, or the matrix A is Hermitian, so therefore I can replace A with A star with A. Okay, now we know that X is the eigenvector that corresponds to the eigenvalue lambda. So we can basically now just go and replace that with lambda x. Okay, and there we go, and that we can replace with lambda x transpose x, and x is a non-zero vector, therefore it has a zero norm. Right, so from there we can then easily say that lambda must be the same as lambda bar. Okay, these are two real numbers, non-zero, they're the same and they're non-zero. This implies that lambda is the same as its conjugate, so therefore lambda must be real. Lambda must be a real number, because a complex number, the only way a complex number can be the same as its conjugate if it is a real number. So therefore lambda is real. Okay, so a Hermitian matrix always has real eigenvalues. Okay, the next one, Theorem 3, if A is a Hermitian matrix, then the eigenvectors from different eigenspaces are orthogonal with respect to the complex dot product. Right, so let's take two distinct eigenvalues and let x and y be respective eigenvectors. Okay, so basically what we do is, again, remember, we've got that AX satisfies that equation. So we take conjugates on both sides. Right, and then what I'm going to do is I'm going to do something. I'm going to multiply on the right and the left with Y's transpose. Okay, so therefore we're going to get this term here. Okay, now just one point. Why am I throwing this away? Why am I throwing that conjugation away there? Because remember we said previously the eigenvalues of a Hermitian matrix they are real. Okay, so the conjugation has no effect on the eigenvalues. So the conjugation there falls away. Right, then again we can just replace this term here with that term there because of the transpose laws. Right, and because the matrix is Hermitian, remember that is now A star, Y, transpose, X bar. And so you can replace that with A, transpose, X bar, lambda 1, Y transpose, X bar. And therefore we can replace AY with, remember, that's now the eigenvalue that corresponds to Y, okay? Okay, now this is a that's a real number, non-zero, and so on the left-hand side, these are distinct eigenvalues. So basically, the only way that can be the same is if you have that that term needs to be zero, which then implies taking conjugates on both sides, we get that y transpose x must be 0, and that is pretty much the complex dot product of x and y, and that must be 0. So eigenvectors from different eigenvalues in a Hermitian matrix must be orthogonal. Okay, so then we've got this little theorem on unitary matrices, right? Very similar to the ones we did previously. If A is an n by n matrix with complex entries, then the following are equivalent, right? A is unitary, is equivalent to saying this is true for all complex vectors, x. That's equivalent to saying this holds for all vectors x, y in Cn. That's equivalent to saying the column vectors of A form an orthonormal set with respect to the complex Euclidean inner product. And also that's equivalent to saying that the row vectors of A form an orthonormal set in Cn with respect to the complex Euclidean product. Okay, so proving that 1 implies 2, let's assume A is unitary. Right, now let's take the norm of the column vector AX squared. Then that's the complex dot between AX and AX. What's the complex dot? It's going to be basically, it's going to be AX conjugation transpose multiplied matrix multiplication with AX. Okay, and that we can replace with that because of the conjugation property. And that can be replaced with X transpose A conjugation transpose dot A. Now, X is unitary. A is unitary. So that means that we can replace this term here with A's inverse. And that is then that. And that implies that that's going to imply that X, or rather say this, that is then going to be, that's going to be X complex dot with X, which is the norm of X squared. And that is going to imply that taking the square root on both sides, and because the norm is always positive, we have that needs to be the same as that. Okay. But if we are to show that 2 implies 3, let's assume 2 is true. So assume the norm of AX is equal to X, the norm of X for all complex vectors, column vectors. And so now we need to prove property 3. So, right now, the important point, if we can show that A's conjugates transpose multiplied by A is the identity matrix, then if we take AX and we dot it with AY, then we know by definition that is going to be AY conjugate transpose AX, and that is going to be conjugate transpose dot AX, and that is going to be that, and this is true, right? So basically you're going to be able to replace that with that. Okay, so basically that is going to be x's dot with y. Okay, so if we can show this, then, and so we're done. So that's all we need to show. Okay, so let's quickly show that I can get that. Okay, so again, this is what we assume, and we want to show that, remember what we want to show is we want to show that A's conjugate transpose A is the identity matrix. Okay, so let's use what we know. So we know that this is true for all vectors in complex vectors X. So we know the square of that we know is that the dot of that with that, and basically that becomes this becomes this by definition, and so this by definition then becomes this, and because that there by assumption is equal to that, we have that this whole thing here is equal to this thing here, because remember what that is just that. Okay, so this is now something we can use. These two things are the same. Now, because this is the same as that from the previous slide, it means this matrix minus this matrix is the zero matrix. Okay. And so basically this is always the zero matrix. Doesn't matter what I make the vector x. I can choose the vector x to be anything. It's always the zero vector. So use this fact now to show that what do I want to do is I want to show that this is the zero vector. The zero matrix, I mean. Because then that will imply that this, if I can show this, right, then that will obviously imply that that is true. Okay, so that is what I want to show. Right, so let's just take this matrix by its own, and let's just let it be the standard n by n matrix with these entries. So all I want to do is I want to show that each one of these entries is 0. Okay, and that's not going to be difficult to do. So I'm going to do that by picking x to be a particular vector. Right, so let's pick x to be the vector that's got zeros everywhere except in the jth position. In other words, the jth row. And let's say the jth row is 1. So I'm first going to show that all the entries on the diagonal are 0, and then I'm going to show that all the entries in every column is 0. That's what I'm going to do. Okay. All right. So now plug x in. Remember, we've got a 1 in the jth position there. So let's first multiply this vector with this whole matrix here, and that is going to be a 1 by n matrix. Okay, so basically the entry in the first row in the first column is going to be the first column here multiplied by, or dot with the first column there. And the only entry I'm going to get is the entry in the jth row and the first column. In the entry in the first row and the second column is basically going to be the first row there multiplied by the second column there, or dot with the second column, and then I'm going to get the entry in the jth row in the second column. And then I'm going to carry this process through. I'm going to get the entry in the jth row in the jth column there, and I'm going to go right up until the end. So essentially I'm getting the jth row of A. Okay, now taking that with that, again, I'm going to multiply that term with that term, plus that term with that term, and I'm going to carry on until I'm going to get to the jth entry there, and I'm going to multiply AJJ with that term there. And so basically, I'm going to get this thing here equal to the zero matrix, or the zero column vector. And so I've got in the jth row here a 0. I've got a 0 there. And that's going to imply that AJJ must be the 0 entry. Okay, so all the entries on the diagonal are 0. So now I'll just show all the entries in each column are 0. And for that, what I'm going to do is I'm going to pick the vector x to be the vector that's 0 everywhere, but in the ith position it's got a 1, and in the jth position it's got a 1. And in this case we assume I is not equal to j. In other words, all the entries that do not lie on the diagonal. Plugging that in again, we need this whole matrix here to be the 0 matrix, and first multiplying this term with that matrix the same way. What we're going to do is we're going to get the entry in the ith row and the first column and the entry in the first row and the first column is going to be the entry in the ith row in the first column of A, plus the entry in the jth column and the jth row in the first column of A. Entry in the first row in the second column is going to be the entry in the ith row in the second column of A, plus the entry in the jth row in the second column of A. And then I'm going to get right up until there, which is the entry in the ith row in the jth column of A, plus the entry in the jth row and the jth column of A. You get right up until there. Vector we're going to dot with that vector there. So plugging everything in, remember there I've got a 0. In the ith position I've got a 0. And again, in that position there, and in that position I've also got a 0 there. Okay, so this is going to imply that this term has to be 0, and we've already proved that these terms on the diagonal are all 0. So that's going to prove that the entry in the ith row in the jth column for I not equal to j is going to be 0. So that means all the entries of the matrix all these A entries are 0. It's going to imply that this matrix is the 0 matrix. Okay? And that is going to imply that this matrix is, if I multiply A with its complex conjugate, it's the identity matrix. Okay, so we're done with that. All right, next we prove that 3 implies 4. And this, again, we assume that 3 holds. That is that the dot of AX with AY is the same as the dot of X with Y. And this is for all complex vectors. Right, so we can let x be the vector x1 up until xn and y be the vector y1 up until yn. All right, so taking the matrix A, there's A. I'm going to pick vectors, go back here. I'm going to pick vectors x and y respectively in a very specific way. Right, so for the vector x, I'm going to pick x to have zeros everywhere except in the jth position. It's going to have a 1 in the jth position, and it's going to have zeros everywhere else. That's my vector x. Now looking at my vector y, I'm going to place zeros everywhere except in the ith position. There I'm going to place a 1. Now if I go and multiply a with x, what essentially am I going to get? I'm going to get the jth column of a. And if I go and multiply a with y, I am going to get the ith column of a. Right, so take note of that. Ax is going to be the jth column of a, and ay is going to be the ith column of a. Right, so taking the vector x, remember the vector x and the vector y respectively, taking them and dotting them separately. So I'm taking x and I'm dotting that with y. So remember x is the vector that has a 1 in the jth position and zeros everywhere else, and y is the vector that's got in the ith position a 1 and zeros everywhere else. Now dotting them separately, you get one of two answers. You will get 0 when I is not equal to j, obviously, okay, and you will get 1 if I is equal to j. That's pretty obvious. Okay, so now taking ax and dotting ax with ay, remember we said if we multiply a with x, we get the jth column there. And if we take a and multiply it with y. Right, so basically if I is not if I is not equal to j, so what this implies is that if I take the dot of two columns, if I take the dot of two different columns, right, then the columns are going to be orthogonal. Columns are pairwise orthogonal. And if I take the dot of a column with itself, if I take the dot of a column with itself, right, then if I take the dot of the column Ci with Ci, that's 1, which is going to imply that the norm of Ci is going to be 1. Okay, so that means all the columns are normal vectors and they are pairwise orthogonal. So they're going to be, it's going to be an orthonormal set of column vectors. Right, so the column vectors form an orthonormal set, which is property 4. Right, let's prove that 4 implies 5. So let's assume A is orthonormal column vectors. Then if we go and look at the matrix A, and I take its conjugate and its transpose, and I multiply it with the matrix A, that has to be the identity matrix, right? Because if I look at this matrix here, A conjugate transpose, and I multiply that with A, remember the conjugate of A's transpose. A's transpose, the rows become my columns and the columns become my rows. So basically, that is going to be my first column, and that same column is going to be my my first row. But I'm going to take the conjugate. I'm going to take the conjugate of that column. So I'm going to take the conjugate of each entry there, and if I dot that, so basically the entries on the diagonal, where the indices are the same, that is all going to have norm 1, right? So that's going to be the same. So you're going to get on the diagonal, you're going to get these ones, and because the column vectors are orthogonal when the indices are not the same, you're going to get zeros everywhere else. Okay. All right. So it's easy. So remember, because the column vectors are pairwise orthogonal and they're orthonormal, when you take this matrix and you multiply it with that, it's going to be the identity matrix. Now, because this is true, okay, it means that A's inverse is this matrix here. So that means also that's going to imply, by a theorem we did in chapter 2, I think, that A, okay, so this is A's inverse. So A with A's inverse is the same as A with A's inverse. It's always the identity. Okay. Right, so take A now. So there's A. And then take the take A's conjugates transpose, right? So basically, we're looking, when we calculate this, we take we start with the first row, and in A's conjugate transpose, the first row is going to be my first column, okay? But I'm going to take the conjugate of each entry there. I'm going to take the conjugate of each entry. And that is just the same as in that example, taking the first row of A and dotting it with the first row of A, and that's the same as taking the first row's conjugate and taking the transpose of that and multiply and dotting that with the first row, and that is, we know that is 1. Okay, so you're going to get, when you calculate all of that, you're going to get ones on the diagonal again. You're going to get zeros everywhere else. So what does that mean? It means that the row vectors are they are normal vectors. In other words, their norm is 1, and the row vectors are pairwise orthogonal as well, because of this fact here that it's the identity matrix. So it's going to imply that the row vectors are basically orthonormal, and it means that the Ri dot with Rj is going to be 0 if I is not equal to j, and it's going to be 1 when I is equal to j. Okay, so therefore 4 implies 5, so the row vectors are also going to be pairwise orthogonal, and they are going to be normal vectors. Okay, and then we can again close the loop by proving that 5 implies 1. Right, so why does 5 imply 1? Why does 5 imply that A is unitary? Well, if the row vectors are pairwise orthogonal and have all norm 1, then it is going to mean that if I take A and I multiply A bar, that with A bar transpose, that must be the identity matrix, and that is then obviously going to imply that A is unitary. Okay, because A's inverse is obviously going to be this matrix. All right, so that those properties are the 5 properties are all they're equivalent. Just a quick application. show that this matrix A is unitary and find its inverse. Okay, so we can apply the previous theorem. So we know all those conditions are equivalent. So to check whether a matrix is unitary, one way we can do that is by using property 4. And all we need to do is show that the column vectors are, they have each norm 1, and they are pairwise orthogonal. Right, so let's take the first column vector and let's go and check the norm of each column vector. So take the dot of the first column with itself. Right, so the dot this is the complex dot product. So that's, you're going to take the conjugate of this matrix transpose, which is this one here. So you're going to change that sign into a negative there. You're going to change that sign into a positive there, and then you're going to dot that with that vector. Okay, so multiplying that out, we get that term plus that term there. Simplifying, we obtain 1. Okay, so the first column, the first column, if I dot the first column with the first column, it's 1. So that's going to imply that the norm of C1 squared is 1, which is going to imply that the norm of C1 is in fact 1. Okay, so first column is a unit vector. So now we take the second column and check whether it's a unit vector or not. Right, so we take the complex dot between the second column and itself. So that is the same as taking the conjugate of this vector, which is there. We change the sign. Okay, and we dot it with that. Okay, right. So that is that term multiplied by that term, which is that term, plus that term multiplied by that term, which is that term there. And then simplifying everything, we get again 1. So that's going to imply that the second column dot with itself is 1, which will imply that the norm squared is going to be 1. And that is going to imply that C2's norm is 1. So both the first and the second columns, they are unit vectors. So to complete, we need to just check that the two column vectors are orthogonal. Right, so let's take the dot of the first column with the second column. So that's the same as taking the conjugate of this transpose, which is this. Change the sign. Well, it's not that, that's a sign there, and then dotting that with this vector here. So it's this term multiplied by that term plus that term multiplied by that term. Okay, so it's this multiplied by that, which is this term here, and that term multiplied by that, which is that term there. And basically working that out, we get this here. From there we have that is 0. Right, so this means that the dot product of the first column with the second column is 0. So that means columns are a it's an orthonormal set. So by our theorem, A is unitary. So its inverse can easily be determined. You just take A, you take the conjugate of A. Right, so we take the conjugate of A, so we change that sign there. Change that sign, and change that sign. Okay, so we've changed all those signs, and then we just take the transpose of that. So taking the transpose, Get our inverse. Right, next we've got unitary diagonalizability. We say a square complex matrix is said to be unitarily diagonalizable if there is a unitary matrix P such that the complex conjugate of P multiplied by A multiplied by P is a complex diagonal matrix, and any such matrix P is said to be unitarily diagonalizable, or any such matrix P is said to unitarily diagonalize A. Now, Theorem 5 states that every n by n Hermitian matrix has an orthonormal set of n eigenvectors and is unitarily diagonalized by any n by n matrix P whose column vectors form an orthonormal set of eigenvectors of A. Now it's important just to remember that the orthonormality mentioned above is with respect to complex Euclidean inner products. So this is the procedure for unitary diagonalizing a Hermitian matrix. So first is you find a basis for each eigenspace of A. Then you apply the Graham-Schmidt process to each of these bases to obtain orthonormal bases for eigenspaces. And then you form the matrix P, whose column vectors are the basis vectors obtained in step 2. And this will be a unitary matrix and will unitarily diagonalize A. And then also to find the complex diagonal matrix D, note that this will be a diagonal matrix whose main diagonal entries will consist of eigenvalues corresponding to the respective columns of P in the correct order. Okay, so it's very similar to the previous chapters, the process for diagonalization. Right, so let's look at unitary diagonalization of a Hermitian matrix. So let's find a matrix P that unitarily diagonalizes the following Hermitian matrix. Right, so let's take our matrix A and find its eigenvalues. Right, so set up my matrix, lambda I minus A. And let's go and look at the determinant of this matrix. Right, so the determinant of that is straightforward. That multiplied with that minus that multiplied with that. Okay, so there you get your two terms. And then simplifying that, we get. Right, so we get this here. And setting that equal to 0, we find our eigenvalues. Lambda equals 0 and lambda equals 3. Right, so the basis for the eigenspace corresponding to lambda equals 0, what you do to get that is you go back to your original matrix and you replace lambda with 0, and you look at the null space of that matrix. So this matrix reduces to that matrix there, and then we look at the null space of that matrix. Right, so it involves getting to the null space, and basically that corresponds to this linear system. And we can parameterize the vector, we can parameterize y as a complex scalar. Right, so the basis for the eigenspace corresponding to lambda equals 0 can be established as this vector here. Then the basis for the eigenspace corresponding to lambda equals 3, you take your original equation and you replace lambda with 3. Okay, and then you go and reduce that matrix and you're looking for the null space. Okay, so that corresponds to the linear system X. And you can go and parameterize Y as a complex scalar. And right, so the basis for the eigenspace corresponding to lambda equals 3 becomes this vector. Right, so I need to just, these vectors correspond to different eigenvalues, so they're obviously going to be orthogonal. We don't have a problem with the orthogonality. We need to make them, they're orthogonal, we just need to make them orthonormal. So we need to go and normalize the vectors. Or that the basis for the eigenspace corresponding to lambda equals 0 is that vector there. So what I want to do is I want to normalize it. So basically we're going to take the norm, and how do we calculate the norm? We are going to calculate the norm by basically taking the square root and dotting the 2. That's the definition of the norm, and that's the norm of the vector of our vector there. So how do we calculate the dot product? In this case, this is how the dot product works. You take the conjugate of this term, which is that, and you take the transpose of that matrix, and then you take the dot product with that. Okay? Right, so that term then becomes this one here, and that is the square root of 3. So I take my matrix, or my vector, basis vector, and I divide it I multiply it with 1 over the square root of 3. At the basis for the eigenspace corresponding to lambda equals 3, what we need to do is we need to find the norm. We need to find the norm of what vector? We need to find the norm of this vector here. Right, so that is going to be, it's going to be the square root of the dot of the vector with itself. So you're going to take the vector and you're going to take the dot with itself. Dot work, you take the conjugate, and you take the dot with that vector. Okay. Right. Right, so multiplying that term with that term, and then adding that to 1, we get the square root of that whole term, and then that reduces to that, and we get square root 3 over square root 2. It can be written as square root 6 over 2. Right, so normalizing our vector, we multiply with 1 over the norm, and so our normalized vector becomes this new vector. Right, so there are my two normalized vectors, the one corresponding to lambda equals 0 and the other one corresponding to lambda equals 3. So now we form our unitary matrix P. And how do we form this matrix? Well, we are going to take our first column to correspond to the first eigenvalue, and we're going to take the second column to correspond to the second eigenvalue, and that is going to be my matrix. And the diagonal matrix is going to be the one with the eigenvalues. Right, so it's going to be the first eigenvalue corresponding to the first column, and it's going to be the second eigenvalue corresponding to the second column, and we have our diagonal matrix. Then this last section on skew symmetric and skew Hermitian matrices that I'm going to leave for you to read through on your own. A skew symmetric matrix, recall, is if its transpose is its negative, and a skew Hermitian matrix is where the complex conjugate is its negative. So go and check whether that given matrix is skew Hermitian. Then lastly, we have normal matrices. Recall that a real symmetric matrices are the only orthogonal diagonalizable matrices. Interestingly, the Hermitian matrices do not constitute the entire class of unitarily diagonalizable complex matrices. Indeed, there are unitarily diagonalizable complex matrices that are not Hermitian. And we say square matrix A is unitarily diagonalizable if and only if A with its complex conjugate is the same as A's complex conjugate multiplied with A. And matrices with the above property are said to be normal matrices. Okay. Right, and I leave the last example for you guys to go and investigate on your own. Give an example of a real matrix which is unitarily diagonalizable but not orthogonally diagonalizable.